I'm honored to introduce to you a leader and a visionary in the memory industry. Andy Su is the founder and CEO of Semiconductor. He has over 3 decades of experience in the semiconductor industry, including positions as VP of Engineering and leader of R&D and engineering teams. This resulted in the development of more than 60 products at various non-volatile memory, DRAM, and AI chip initiatives. Andy is an accomplished technology visionary and inventor of 125 granted U.S. patents. He has done significant amount of performing research in the fields of neural networks and artificial intelligence, while earning a master's degree in electrical computing and systems engineering from Rensselaer Polytechnic Institute in New York. He earned a bachelor's degree from the National Chung Kung University in Taiwan. Every year, NEO seems to bring some type of new innovation for the keynote address, and I'm wondering if there's going to be something of a special surprise today. There's going to be a short video, and then please join me in welcoming Andy Su.
From day one, NEO Semiconductor set out to break the biggest barrier in AI, the memory bottleneck. We knew tweaks wouldn't cut it, so we built a bold roadmap and delivered step by step. 2020, XNAND, accelerated storage speeds. 2023, 3D XDRAM, expanded memory capacity. 2024, 3D XAI, enabled in-memory computing. 2025, XHBM, shattering bandwidth limits and unlocking the true power of AI chips. In 2026, NEO's AI Core will be launched to accelerate GPU's processing speed. A proof-of-concept test chip for 3D XDRAM is now in development. These breakthroughs are the result of decades of pushing memory to new heights. We're proud of how far we've come and excited about what's next.
Last year, on this stage, I promised to share an update about our 3D XDRAM test chip. Today, I'm proud to present here one of the first test chip wafers from our 3D XDRAM, produced somewhere in Taiwan. So we promised and we delivered. Good morning, everyone. I'm Andy Su, the founder and CEO of NEO Semiconductor. In this keynote presentation, I will share with you how we're transforming the future of AI computing. Current HBM stack 12 to 16 DRAM dies to achieve high density. Each DRAM die contains 24 to 32 gigabits of the DRAM cells, resulting in a total capacity of 48 to 64 gigabytes per HBM. To connect these DRAM dies, a technology called through silicon via, TSV, is used to create vertical metal connections passing through the dies. These TSVs are connected to a controller chip, allow the data to be transferred from each DRAM dies to the controller chip and then to the GPU. Because each DRAM die is about 50 micrometers thick, TSV must be as wide as 5 micrometers to penetrate the die. This large TSV not only increase the die size, but also limited the number of the TSVs can be integrated. So even with the most advanced HBM generation, HBM4, the number of TSV is kept at around 2,000 bits. That's simply insufficient to fulfill the future of the AI applications. So today's HBM faces two major bottlenecks. First, its capacity is hard to scale beyond 64 gigabytes. Second, the bus width is hard to extend it beyond 2000 bits. These memory bottlenecks limit the performance of the AI chips. To meet future AI demands, we need a new memory architecture, one that can scale beyond the limitation of today's TSV. This is why Semiconductor created the XHBM, also called the XBM, meaning extremely high bandwidth memory. It's a revolutionary technology that can overcome the bandwidth limitation of today's HBM. XHBM is based on Semiconductor's 3D DRAM technology, which forms a 3D NAND-like array with hundreds of layers of the DRAM cells on the surface of a single die. With current technology, it can achieve 300 layers, delivering the density of 300 gigabit, which is 10 times higher density than today's DRAMs. And in the future, it can be extended to over 500 or even 1,000 layers. Can you imagine one day, a single DRAM die could reach 1 terabit density? And these 300 layers of the DRAM cell are interconnected by billions of metal lines called vertical B-lines. These vertical B-lines serve as data buses, allowing gigabits of data to be transferred through these lines and eliminating the need for the large-size TSV. To connect these vertical B-lines, the die is flipped and bonded to a controller chip using hybrid bonding technology. Hybrid bonding is an advanced interconnection technology with 0.5 micrometer pitch, only 10% the size of TSVs, so which can dramatically increase the bus width from today's 2,000 to 32,000 bits, resulting in a 16 times increase in the bandwidth. Besides increased bus width, it also reduces the data latency and the power consumptions. Because each cell layer is very thin, it's about 70 nanometer thick. So the entire 300 layers are only 20 micrometers tall. This dramatically shortens the data bus, thereby reducing the data latency and the power consumptions. As a result, a single XHBM can replace the 16 DRAM dies used in today's HBM. This reduces the die cost, data latency, and the power consumptions. For comparison, traditional HBM with 16 DRAM dies are about 600 micrometers tall. That's 30 times taller than XHBM. So it takes much more power and time to transfer data through these long TSVs. It's like comparing the 30-story skyscraper to a single-story house. The single-story house, of course, is faster and more energy efficient to transfer data. As a result, XHBM technology can overcome the bottleneck of today's HBM and increase the bus width by 16 times from 2,000 to 32,000 bits. Isn't this amazing? This can dramatically boost the performance for the next generation's AI chips. With XHBM, we can achieve many advantages, including higher bandwidth, lower power consumption, shorter latency, lower package height, and smaller footprint. So it's a true game changer for AI memory. Besides that, because HBM is so thin, it can be directly bound onto the GPU die without compromising heat dissipation. This enables a true 3D integration. It allows the ultra-high-speed data communication between GPU and HBM to maximize AI performance. Besides HBM applications, this architecture can be also combined with Neo Semiconductor's XNAND technology to create an extremely high bandwidth flash memory called XHBF. It uses a 3D NAND flash memory array to provide a high density, high bandwidth, non-volatile data storage for large models, making it particularly suitable for in-memory computing. Now, you might be wondering, how is this all possible? The secret is 3D XDRAM. At the heart of XHBM is Neo Semiconductor's groundbreaking technology called 3D XDRAM, which is the first 3D NAND-like DRAM array. This array has been proven by over a decade of high-volume production of 3D NAND flash memory. That's why we choose this mature process to implement our 3D XDRAM. We introduced our 3D XDRAM in 2023, starting with 1T0C floating body cell. Since then, we've expanded into a full family of cell structures. In 2025, to meet the broader market demand, we added two new cell structures, the 1T1C and 3T0C cells. The original 1T1C cell contains only one transistor, and the new 1T1C cell contains one transistor and one capacitor, while the 3T0C cell contains three transistors. With these three cell types, we ensure compatibility with the diverse technology roadmap of DRAM manufacturers worldwide. The first 1T0C cell is based on floating body cell technology. It stores electric charge in a floating body to represent the data. This eliminates the need for a large capacitor and creates a unique 3D NAND-like cell structure. The proof of concept for this test chip is currently in progress. In contrast, the new 1T1C cell is based on traditional DRAM design. It integrates one transistor and one capacitor into a single cell. Unlike other 1T1C DRAM that use an extra large capacitor, this cell forms the capacitor on the sidewall, resulting in a much more compact cell structure. To write the data, the transistor is turned on to allow electrons flowing through its channel, and then stored in the capacitor formed at the sidewall. The transistor channel can be made of silicon or polysilicon. However, for optimal performance, IGZO material can be used to minimize leakage current and greatly enhance data retention. We verified this new cell structure and its operations through TCAD simulations. This diagram shows the distribution of electron concentrations. It demonstrates the cell can achieve fast read and write speed within 10 nanoseconds. When the channel is turned off, The IGREO's extremely low leakage current enable ultra-long data retention time for over 400 seconds, making it an excellent solution for both HBM and low-power applications. The other new member, the 3T0C cell, is specifically designed for in-memory computing. It features a unique 3-transistor structure. These transistors are integrated into a compact 3D NAND-like cell structure. To write the data, the first transistor is turned on to store electrons in the gate of the second transistor, which enable current to flow through the channel, and then the third transistor select which cell to be read. This cell allows it to be read without disrupting the stored data, making it particularly suitable for in-memory computing. Now listen to this. The most important part is these cells are manufactured using a traditional 3D NAND-like process. For 1T1C cell, here's are the steps. 1. Stacking multiple polysilicon and nitride layers. 2. Etching benign holes and recessing the polysilicon layers. 3. Depositing dielectric IGZO and nitride layers. 4. Re-etching the benign holes and filling it with metal. 5. Etching nitride layers and depositing electric layer and metal layers. Then the cell array is complete. This streamlined process uses only one mask to process all the 100 layers simultaneously. This eliminates the most critical misalignment challenge in 3D arrays. This is the key to realize 3D DRAM technology. Now, let's take a look at the performance boosting that 3D XDRAM can bring to AI chips. Traditional 2D DRAM increased density by shrinking cell size, but it's already approaching the scaling limit. The current density for 2D DRAM is 24 to 32 gigabit. Projection shows its density may reach only 48 gigabit at the 0A node. In contrast, 3D XDRAM increases the density by stacking more layers. With current technology, it can achieve 300 gigabit density with 300 layers. And in the future, estimation shows it can achieve 500 gigabit with 500 layers, offering 10 times higher density than traditional 2D DRAM. Besides density, XHBM also delivers a dramatic boost for bandwidth. The current HBM offers a bus width around 1000 bit. Even the next generation HBM4 is expected to reach only 2000 bits. XHBM can increase the bus width by 4 to 16 times, up to 32,000 bits. Can you imagine that? Can you imagine how much this will improve the performance for AI applications? Together, these three cells offer broad compatibility for diverse market needs. The 1T0C cell is suitable for both HBM and in-memory computing. The 1T1C cell provides extremely long data retention time for low-power applications such as wearable and AOIT devices. The 3T0C cell is designed for in-memory computing in edge AI applications, including smart camera and drones. From day one, Neo Semiconductor set out to solve one of the biggest challenges in AI, the memory bottleneck. We knew this wouldn't be solved by small improvement, but required bold innovations. So we built a roadmap and deliver on it step by step. We introduced the XNAND to improve data storage speed. Then 3D XDRAM to overcome the capacity limitation. Then 3D XAI to enable in-memory computing. And now, XHBM will shatter memory bandwidth limitation, unlocking the full potential for AI chips. Next year, we will introduce a new technology for AI processing core that delivers 5 to 10 times the performance of today's GPU core. These breakthroughs are made possible by a team that has spent decades pushing the boundary of what memory can achieve. We are proud of how far we have come and even more excited about what we are going. And we invite you to join us to reshape the future of AI computing. Thank you.